Okay, so I know we did most of the notes in class already together, but let me go ahead and just record from the beginning. You can choose whether to fast forward it or however you want to watch the notes, but this way all of the notes will be available for everyone. Okay, so let's go ahead and let's begin. It says chemical reactions. The abbreviation for reaction is RxNS, or chemical changes, is the process by which the atoms of one or more substances are rearranged to form new substances. It says here there are a few signs that a chemical change had occurred. Number one, gas was produced. A formation of a precipitate, which is a solid, was formed. It will gain or lose energy. When that occurs, light will be produced and light or temperature change can occur, one or the other, or both. Number four, change in color. And an odor formed. So if any one of those has occurred, then that's an indication that a chemical change reaction has occurred, meaning that one or more atoms stopped, broke apart, somehow rearranged, and became back together, and it's something new. So chemical equations. It says here on a chemical equation, a chemical reaction is represented by a chemical equation using words or formulas. Parts of a chemical equation. Well, we have the reactant part, which is the beginning, right? What you start off with of those substances, to what we call the base of the arrow. And we have the product substance. It's the substance that is made. M-A-D-E. The new stuff that's produced from it. And that's going to be at the point of the arrow. So I'm going to have the reactants, which is at the base of the arrow. And then I'm going to have what we call the products, which is at the point of the arrow. It does not always, but normally it goes from left to right. Sometimes it could go from right to left. Arrow. The actual arrow shows the direction in which the reaction process is taking place. We call that arrow a yield sign, okay? A yield. So when we say the word yield, we mean arrow. It says here, let's talk about a few of the physical states that are going to occur. You're going to see solids represented as an S. You're going to see gases represented as a G. L stands for liquid. And AQ stands for aqueous. An aqueous is used when a substance is dissolved in water. So word equation examples. So writing out burning carbon in the presence of oxygen forms carbon dioxide is quite long. And in chemistry, we don't want to sit there and write all of that together. That's just too much. So let's go ahead and let's abbreviate or shortcut this. Burning carbon in the presence of oxygen forms carbon dioxide. So let's go ahead and let's write that, and we're going to shortcut that. Carbon plus the presence of oxygen. What is oxygen? Oxygen's a diatomic, so let's put a little 2 there. Forms our product, which is carbon dioxide. Means that there's 2 oxygens. Okay? Now, when we do this, this is called our skeleton equation. Then we can go back and we can double check to make sure it's balanced. Now, the next example here, it says we've got 5 grams of carbon reacts, which is our plus sign, with 5 grams of oxygen to form, that's our arrow. How much carbon monoxide? Well, 5 plus 5 equals 10. Because due to the law of conservation of mass, the amount I have before, which is 5 plus 5, better yield how much I end up with, which is 10. So let's go ahead and let's do that. It says here, skeleton equations are not always balanced. So carbon, 5 grams of carbon plus 5 grams of oxygen, oxygen's a diatomic, put it 2, yields 10 grams of carbon monoxide. Okay? So don't forget, a lot of times when we go ahead and write that down, all of this is just going to be a skeleton equation. That's what we call it, a skeleton, because it's just the basic part of it. It's not balanced. Let's go ahead and let's turn the page and let's continue with these notes. The conservation of mass. Now, the conservation of mass tells me the amount of matter I start off with before needs to equal the amount of matter I'm going to have afterwards, which actually makes sense. If you're going to make a cake and you open up the box and it says you need 2 eggs, you need some cooking oil and some water, mix it together, put it in the oven. How many cakes are you going to get out when it's done? You're going to get 1 cake. You used 1 cake box, you're going to get out 1 cake. Right? You're not going to put it in the oven and have 7 cakes come out. That doesn't make sense. So however much you start off with ends up with the same amount. So the law of conservation of mass says in a chemical change, matter is neither created nor destroyed. Bonds can be broken and reformed into new products, but the amount of matter present at the start of the reaction must be the same as the present at the end, as was present at the end. So however much I start off with needs to equal at the end. Now let's talk about balancing chemical equations. Due to the law of conservation of mass, we need to learn how to balance chemical equations. Now, it says here, each side of the equations must have the same number and the same type of atoms of each element. Right? So let's go ahead and let's look at this example. H and O yields H and O. All right? Now this is our skeleton equation, and then we're going to come over here and we're going to balance it. We can't end up with H and O yields carbon and oxygen. That doesn't make sense. Unable to do that. Now the subscript is the small number, and it tells you how many atoms of each element are in the compound. The coefficients are the numbers in the front, which are the big numbers, which provides the lowest whole number ratio of the amounts of the reactants and the products. Okay? It says here, let's look at some of the steps when it comes to balancing chemical equations. Number 1, write a skeleton equation using the correct formula for all of the reactants and the products. B, count the number of atoms of each element on the reactants and the products separately. Polyatomics, it says here, unchanged on both sides, count as one single unit. Remember, we did that already, but again, I'm just reviewing and going back over the notes. If the polyatomic on the right side is the same polyatomic on the left side because it did not separate, then we just count it as one whole one. But if the polyatomic is going to separate and then break apart and do something, well then in that case, let's go ahead and break up every element in that polyatomic and count everything separately. It says here, change the coefficient number to make the number of atoms on each side equal out both the same. Do not ever change the subscripts, okay? That subscript is what it is, okay? Which is the little number. You can only change the big number in the front. D, make sure that the coefficients are at the lowest possible ratio. If need be, then reduce it. And then it says here, double check. Make sure that everything balances out. So let's practice this. So I have zinc, I have hydrogen, I have sulfur, and I have oxygen. Now, I see that sulfur and oxygen right here is actually a polyatomic. And on this side, the sulfur and oxygen, okay, is also there as a polyatomic. Because it stays a polyatomic and doesn't separate, then when I go ahead and I start to balance, I'm going to leave it as a polyatomic. So let's write down our elements. We have zinc, we have hydrogen, and we have SO4. I'm going to draw my wall. My wall is going to separate my reactants versus my product side. And I'm going to go ahead and count. As of right now, right there, it's just blank. There's actually a number there. It's invisible. It's the number 1. And behind every element is a number. Whether there's 1 or not. This number, it's missing, but it's invisible. It's a 1. Behind the H, there's a 2. SO is going to be considered to be one whole thing. Even though it has 4 oxygen, SO4 is one bonded compound. Okay? So let's look. 1 times 1 is 1. Hydrogen, 1 times 2 is 2. 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. 1 times 1 is 1. Let's double check this. 1 and 1, 2 and 2, 1 and 1. I am balanced. Now here's where you have your option. You can choose to go ahead and write the number 1 in front of all of them. And that way, at least you know, okay, I've done that one, that problem, I can move on to the next. Or you may see it sometimes just left blank, because leaving it blank means that there's an invisible number 1. Let's go to letter B. Sodium hydroxide plus calcium bromide yields calcium hydroxide plus sodium bromide. So let's go ahead and let's do that one. First thing is, I'm going to go ahead myself and I'm going to put sodium, which is Na. It's a metal, so it has a plus sign, and it's in group 1, so it's a plus 1. Hydroxide is a polyatomic, which is an OH, and it has a negative 1. Calcium is a metal, Ca, and it's in group 2, so he has a plus 2. And bromide, which is bromine, which is Br, it's a non-metal and has a negative 1. Calcium is a metal, plus 2. Hydroxide, which is a polyatomic, OH, negative 1. Sodium, Na, it's a metal, plus 1. And bromide, which is bromine, which is a non-metal, negative 1. Now, because I have metals in here, what am I going to do? I'm going to crisscross. So let's please make sure that we do that. Crisscross. Those ones are going to cancel out. Crisscross. Crisscross. And again, those ones are going to cancel out. So let's go ahead and write the actual equation the right way. This is going to be NaOH. That OH is a polyatomic. That's going to be stuck together right here. Then plus, we're going to have, and that's an aqueous, calcium bromide. Ca, the 1 crosses over, so I'll leave it blank. Br, and the 2 crosses over. Calcium hydroxide. Okay, so my polyatomic on this side is going to stay the same polyatomic on that side. Ca, the 1 crosses over, so leave it blank. OH, wait a minute. The 2 is going to come over, so what do? I use parentheses, and then I put the little 2. Sodium, Na, Br. Those ones cancel each other out, and they're invisible. So here's where I'm at. Let's go ahead and let's balance. Here's my yield sign, and let me go ahead and write my Na. OH is a polyatomic on both sides. OH, Ca, Br. Draw my wall. Now let's go ahead and let's start multiplying. 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. 1 times 2 is 2. Let's do the product side. 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. 1 times 1 is 1. Am I balanced? No, I'm not. I'm not balanced here, and I'm not balanced here. So let's go ahead and let's do something to this. What can we do? The only thing we can do is add the number in front, right? which is the coefficient. So let's do that. I'm going to, the OHs, the hydroxide on this side needs more. So let me put a 2. Now when I do that, before I go any further, I like to go ahead and let me double check. 2 times 1 is 2. 2 times 1 is 2. Am I balanced? Well, now I'm okay here, but this one now is out of whack, as well as the BRs. So let's come over here to the product side, the NA and the BRs. They actually are stuck together, and I'm going to put a 2 because I need more sodiums on the product side. Let's go ahead and balance it. 2 times 1 is 2. I'm sorry, I meant to say let's count it out. 2 times 1 is 2. So now let's check. 2 and 2, check. 2 and 2, check. 1 and 1, check. 2 and 2. I am balanced. You have an option. You can go ahead and put a number 1 in front of those, or you can just leave them blank. Your choice. Let's turn the page and let's keep going and practicing with this balancing chemical equations. I know we did it in class. Again, like I said, your choice. You can more than welcome skip over this part if you prefer. Let's come over here. I have iron and I have chlorine, and then I have sodium and I have hydroxide. But on this side I have hydroxide, so they actually stay together. They don't break apart. So let me go ahead. Iron, Fe, chlorine, Cl, sodium, Na, and hydroxide, OH. Let's draw my wall. I'm going to go ahead and I'm going to start my multiplication of C. 1 times 1 is 1. 1 times 3 is 3. 1 times 1 is 1. 1 times 1 is 1. Fe. 1 times 1 is 1. 1 times 3 is 3. 1 times 1 is 1. 1 times 1 is 1. Am I balanced? No, I'm not. The chlorines and hydroxides are not balanced. I need more chlorines over here. I need more hydroxide. I actually need 3 chlorines. So let me go ahead and put a 3 in front of it. But let me go ahead and remultiply so that way I can balance again. 3 times 1 is 3. 3 times 1 is 3. Now my chlorines are better, but let's look. My NAs and my OHs now both are not balanced. So let's come over here. Na, and look at this. The OHs are actually attached to it, which makes it great. Let's put a 3 in front of it and let's remultiply. 3 times 1 is 3. 3 times 1 is 3. Am I balanced? Let's check. 1 and 1. 3, 3. 3 and 3. 3 and 3. I am. Okay? I am. So let's go ahead and let's look at the next one. Carbon disulfide reacts with oxygen to produce carbon dioxide and sulfur dioxide. So let's go ahead and let's do that. I'm going to first write out my stuff. Carbon disulfide. Carbon disulfide means that it's sulfur, but I have a little 2 behind it because of the di. Reacts which is plus, oxygen. But wait a minute. Oxygen is a diatomic, so let's put a little 2. Produces, which is the yield sign, carbon dioxide, carbon and oxygen, but there's a 2 behind of it because of the di, and sulfur dioxide, O2. Let's go ahead and let's check to see if we're balanced. I have carbon, I have sulfur, and I have oxygen. Draw my walls. Now let's do our multiplication. 1 times 1 is 1. 1 times 2 is 2. 1 times 2 is 2. 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. 1 times 2 is 2. I have oxygen and oxygen over here. They're actually separated, so I need to add them together. So the rule it says here is the number of elements of the same kind get added together when they are in different compounds. So this rule is being used over here on part D. How oxygen and oxygen, they're the same element. They're separated, so I need to add it. 2 plus 2 actually equals 4. Am I balanced? my sulfur and my oxygens are not balanced. I need more oxygen on this side. I actually needed to say 4, and I have 2. So 2 times something is 4. 2 times 2. So let's go ahead and write that in. Let's multiply. 2 times 2 is 4. The oxygens and carbons are okay, but my sulfurs are not. On this side, I need more sulfur. So let's go ahead and let's write a 2. And let's remultiply. 2 times 1 is 2. But 2 times 2, plus don't forget that. So what I'm going to do is I'm going to mark all of this out and recount the oxygens all over again. 1 times 2 is 2, plus 2 times 2 is 4, which equals 6. Am I balanced? No, I'm not. My carbons are good, my sulfurs are good, my oxygens are not. I need 6 oxygens on this side, and I actually have 4. So if I take away that number 2, 2 times something is 6, right? What can I put on here? 2 times 3 is 6. Let's check. 1 and 1, 2 and 2, 6 and 6. I am balanced. I can move on to the next step. The next step one here was that weird one that we did in class. Aluminum nitrate, it says here, decomposes, which means breaks apart, to form dinitrogen monoxide and water. So ammonium nitrate, those are 2 polyatomics, okay? Ammonium nitrate. I don't have a lot of space up here, so I'm going to go ahead and just rewrite it down here. You know what? I'm just going to do it this way. Oh, you know what? I have enough space. I apologize. NH4NO3. NH4NO3. NH4 is ammonium, NO3 is nitrate. Those are the polyatomics. Decomposes, which means breaks apart to form dinitrogen. What does dinitrogen mean? Dinitrogen is going to be, dinitrogen monoxide. So nitrogen, which there's going to be 2. I apologize because it should have been over here. So nitrogen with a little 2, monoxide, which is oxygen and only 1, and water. We got that one, H2O. Let's go ahead and let's do our balancing. I'm going to have, I have polyatomics, but over here, do I have polyatomics that are the same? Actually, I don't. They break apart. So since they break apart into individual elements, let me go ahead and let's do it individually. I have nitrogen, I have hydrogens, and I have oxygens. Let's draw our wall. Start off on this side. I'm going to separate each element separately. Okay? How many nitrogens do I have? 1 times 1 is 1. 1 times 1 is 1. So I actually have 2 on this side. I have 4 hydrogens, and I have 3 oxygens. Over here on this side, 1 times 2 is 2. 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. Am I balanced? No. I need more hydrogens on this side, and I need more oxygens on this side. Now I need to go ahead and I got to find another number. Let's go a little bit bigger, because if there's a 2 now here, then 2 times something is 4. So if I put a 2, because 2 times 2 is 4, let's recount it. And 2 times 2 times 1 is 2. But wait a minute, look at this one. 1 times 1 is 1, plus 2 times 1 is 2, which equals 3 oxygens. Let's go ahead and let's check it. 2 and 2, 4 and 4, 3 and 3. Okay? That was a little one that was a little bit weird that we did in class, but the next one I think is the weird one, right? So let's look at this one, letter F. Letter F says C6H6 liquid plus O2 gas yields CO2 gas plus H2O gas. So step number 1, do I see anything about polyatomics? No, I don't. Great. Let's write out my elements, C, H, and O. Draw my walls to separate the reactants versus the product side. Let's come over here and let's start multiplying. 1 times 6 is 6. 1 times 6 is 6. 1 times 2 is 2. This side. Carbon. 1 times 1 is 1. Oxygen. 1 times 2 is 2. Hydrogen. 1 times 2 is 2. Oxygen. 1 times 1 is 1. Am I balanced? No. All of them are not balanced. Well, on this side, I need more carbon. I need to have 6. So 1 times something is 6. Let's go ahead and let's write a 6 here. Now let's recount. 6 times 1 is 6. Carbon. I'm sorry. That was carbon. Oxygen. 6 times 2 is 12. Whoa. Plus 1 times 1 is 1, which equals 13. Whoa. I am definitely not balanced. I've got the carbons are good. The hydrogen needs to be more on this side. And my oxygen, I have this weird odd number. Well, let's come over here to hydrogens. I need to have it to be a 6. So 2 times something is 6. 2 times 3. So let's go ahead and recount. 3 times 2 is 6. But don't forget this oxygens that are separated. 6 times 2 is 12 plus 3 times 1 is 3. Now I have, whoa, it's still an odd number. I have 15. My hydrogen carbons are good, but my oxygens are not good. Okay? So let's come over here and let's take a glance on this side. What can I do? Well, when I get a weird number like this, an odd number, right, that 15, I just need to go ahead and think about, well, what can I do? I need to decide, is there any way I can make this a 15? What do you think? Can I, 2 times something is 15? No, 2 times nothing is 15 because 2 is an even number and 15 is an odd number. I can't do that. But what if I come over here and I look at this and I say, well, could I go ahead and actually change something? What if, and I know we don't like to go with big numbers. We like to keep the numbers as small as possible. But what if I actually write a 15 here? And I say 15 times 2. What is 15 times 2? 30. 30 is an even number. So let's see if we can make this a 30 over here. Well, if I do that, now on this side, I've got 15. But this is 12 over here. Because 6 times 2 is 12. And 3 times 1 is 3, which equals a total of 15. What if I go back and I change a little bit on this side? What if I say, well, let me come along over here and let me change this oxygens a little bit. What if I go from a 3 times 1 is 3, but I'm trying to make it bigger. What if I go 4? 4 times 1 is 4, and that would be 12 plus 4 equals 16. No, that's not going to work. This is 30. I need this to be 30. Let's look at the next number. Instead of 4, let's go to a 5. 5 times 1 is 5. So this is 12 plus 5. That would equal 17. That's an odd number. We don't like that. Let's keep going. 5 is not going to work. 6. 6 times 1 is 6. So 6 plus 12 is 18. Well, at least I'm getting to an even number a little bit better. So I'm going to go ahead and I'm going to scratch this out and I'm going to put a 6. Now this becomes a 6. And I'm going to go ahead and just scratch the whole thing. 12 plus 6 equals 18. That's still not happy. But look at this. Hydrogen becomes 6 times 2 is 12. Whoa. Now on this side, my hydrogens are 6. So before I go any further, where I'm at right now, and before I make this number any bigger, let's kind of help out the oxygens a little bit on the reactant side. So on the reactant side, it needs to be a 12, but it's a 6. So 6 times something is 12. 6 times 2. So let's go ahead and recount. 6 times 2, 2 times 6 is 12 carbons. 2 times 6 is 12 hydrogens. Hydrogens are good. Oxygens are still not good. But look at my carbons. They're not good. This is a 6 and this is a 12. So this carbon right here has the number 1 in front of it. I need it to become a 12. What can I do? What number can I put in front of it to make a 12? 1 times something is 12. 12. 12 times 1 is 12. But wait a minute. Let's look at this. 12 times 2 is 24. 24 plus 6 equals, what does 24 plus 6 equal? 30. Whoa. I made it. I don't have to go back and mess with this number anymore. This one did it for me. So let's check. 12 and 12, 12 and 12, 30 and 30. And that was a really weird one. Okay? Let's keep looking because we've got more practice. We've got to practice one here, and then we're going to get into the reaction types. So let's practice this one more time. It says here, trick. If you break water into hydrogen and OH, it is sometimes easier to count. Whoa. Why are they saying that? I have lithium and I have H2O, which is water. But look on this side. I have OH and I have H's. So they're actually broken apart. So because of that, it says it might be easier to count the H2O broken apart. So let's write lithium because I have lithium. And on this side I have H2O. On this side I have OH and H. So if I break this water apart to a hydroxide and hydrogen, it's going to be a little bit easier. So let's go ahead and do our multiplication. 1 times 1 is 1. 1 times 2 is 2. 1 times 1 is 1. Let's keep going. On this side, lithium, 1 times 1 is 1. Oxygen, 1 times 1 is 1. Hydrogens, I've got